Okay, so what we're going to talk about in the remaining 20-ish minutes of the lecture is basically we're going to look at nested loop join a little bit. We're going to look at its performance characteristics as far as I/O is concerned. And then if we have time, which we'll probably have to do this on next Monday, is we'll start talking about other join algorithms that are actually more efficient. So this was nested loop join. Go through the tuples in R, go through the tuples in S. If two tuples can join, then output the join of them. So that's pretty easy. And the reason why it was funny, because I had this meeting that I had this morning was a stand-up meeting for a software programming project. And the guy was like, I hate nested loop join. It is the worst, ugliest, most hideous join algorithm ever. And I said, but it's generic. You can do any join predicate on it. So every database that wants to be generalized has to support nested loop join. So it's a good algorithm. It's actually, you want to have nested loop join because it's a fantastic fallback for situations where you can't do anything faster. So that's why we always want to have nested loop join. And so like I say here, we're going to look at the I/O cost a little bit. And so we have these two tables R, okay? And table R has some number of blocks and it has some number of tuples, which I actually had on the previous slide. So n sub R is the number of tuples in R, b sub R is the number of blocks in R, n sub S is the number of tuples in S, and b sub S is the number of blocks in S. So here's the question. How many large disk seeks will be required by this join algorithm? That's one of the questions. Remember, we're talking about magnetic disks. This is not a question if we're talking about solid-state drives. And all of you will probably notice that with your solid-state drives, this join algorithm is fine. And if you ran this on a magnetic disk, you would probably be able to go get lunch and come back and look at the output of NanoDB because of the disk seeking. And the other question is, how many block reads will the operation perform? Okay. Now, we have this assumption that both R and S fit entirely within memory. But they aren't in memory yet. We have to assume that R and S are not in memory yet. They get loaded as the algorithm runs. So we have R and S. So seeks. What's going to be the first seek that occurs? And we're talking about large seeks, not small seeks. So what's the first large seek that will occur as this algorithm runs? It's a really obvious one. Yes? We don't have T here. We have R, yeah. So we have to get the first page of R, right? We have to go and get the first tuple in table R, so we need to get the first block out of R. Then what's the next big seek? Yeah, we have to get the first block out of S. Now, what's the next seek? Let's presume, we could do all these cool disk optimization or disk I/O optimization. Let's pretend we're really naive and we don't know how to do any of that stuff. So what would be the next seek in this situation? Like just by looking at the algorithm. Yeah, well not next row because we're presuming that our blocks contain multiple rows, right? So, but it's the right idea because what are we doing in the inner loop? We're scanning through S, right? So the next seek that we do will be to get the second block in S. But what was the previous thing that we loaded? It was the first block in S, so that's a small seek. And then we load the next block in S, next block in S, all the way through. So we read through S. Now remember, R and S fit entirely in memory. This is the assumption here. So we load S into memory. Any subsequent access to S no longer needs to touch the disk because it's already in memory. So what's the next big seek? Yeah, we have to get the next block in R. So once we've done all the tuples in R, now we need to get the next block in R. And for each tuple in R, we're scanning all of S because of the way we've written our stupid, hideous nested loop join algorithm. But S is all in memory, so we don't need to touch the disk at all. So the next block in R, and then after we've loaded that block in R, next block in R, next block in R, those are all small disk seeks. So very interesting. So like I say, probably one large seek to read the first tuple in R, another large seek for reading the first tuple in S. Then we have a whole bunch of small seeks, which are inexpensive compared to large seeks anyway. They're still expensive compared to accessing RAM. And then we go back to read the second block of R, and then we read all the blocks in R. Okay? So when you tally this up, look at the long arrows versus the short arrows. We're being simplistic here, but let's just look at the long arrows. And so we have, how many blocks are read? Well, we read all the blocks that we need. So B sub R plus B sub S for the number of block reads. And we have 2 to 3 large disk seeks. Now, it's possible that the disk head is already over R, and that's why I say 2 to 3. But let's presume the worst case, then we're going to say 3 large seeks. Okay? This isn't too bad. This is our best case with nested loop. Now let's say that the database can only hold 1 block of each table. So I can only hold 1 block of R and 1 block of S. And I'm sad. So how many block reads are required? Ooh, very good insight here. We want to look at which table is smaller. So we will. And that's an important consequence of this analysis. But it's interesting because there's some caveats. But we'll get to that. I don't want to get ahead of the story. But that's a very good insight. How many block reads are required? So let me ask you this. How many times do we scan through S? BR, NR, BS, NS, some other number? How many times do we scan through S? Is it each page? It's for TR and R. So T's are starting to run down. NR is the number of times we scan through S. And remember, we can only hold 1 block of S at a time. So we read the first block of S, and then we read the second block, and that replaces the first block. And then we read the third block, and that replaces the second block. It's terrible. Our lives are miserable. Or, I mean, the NanoDB's life is miserable. So we read through this. So we do B sub S block reads for every scan through S, and we scan through S N sub R times. Now, how many block reads do we do for R? We can always hold 1 block of R, but it's in the outer loop. So we do B sub R block reads, right? Everybody see that? So this is terrible. Okay, S is scanned once per tuple, so we hop through S, and each time it replaces the previous page. Then we go to the second tuple in R, and we have to go back and scan through S again. Yay, for lots of disk I/O. And then, of course, we finish, let's say we finish the first block of R, now we have to go load the second block of S, and then we rinse and repeat, and we go through the process again. There was no way I could draw all the arrows in the picture, so hopefully that is enough arrows for representative indication of how horrible it is. Okay, so outer loop performs B sub R block reads, inner loop is once per tuple, and so you can see B sub R plus N sub R times B sub S. Now, again, disk access is on the order of, let's say, 5 to 30 milliseconds if you're talking about a hard disk. This is terrible. This is horrible. We need RAM to make this fast. Solid-state drive, we're talking on the order of tens of microseconds. This is still pretty awful. Okay? The one nice thing is that at least seeks go away, so it becomes substantially faster than on a disk, but still, it's terrible. Okay, so how many large seeks are required now? Well, the appropriate way of looking at this is, how many of my seeks are small, actually? Which ones of my seeks are small? Because I basically have a whole bunch of reading I'm doing, but you can see which arrows are large and which arrows are small, right? Yeah, we're presuming that R and S are laid out on the physical platter in some defragmented way. So you can see that scanning through S, small seeks. But every time we go to the start of S, we have a big seek. Either, after reading a block from R or reading the last block in S. So we go back to the beginning. How many times do we go to the beginning of S? N sub R. Once for each tuple in R. And for each block in R, we have to seek again to go read it because we were busy reading other things. So how many large seeks are we going to require? So I guess here inner loop traverses S sequentially, so we have once per loop at the beginning. And the outer loop traverses R in blocks, so we have BR total seeks. So we have B sub R plus N sub R. And since this is the slowest part of the disk's behavior, you can see that this is terrible. Nested loop is awful when we don't have memory to do it. Thankfully, that's not a problem anymore because we have so much memory. But boy, if you have no memory, this is just terrible. This is also why when we cost nested loop, we kind of plan for the best case. Okay? Now, let's say that only S fits in memory. R doesn't fit in memory. We can only hold one block of R, and S, the entire thing of S, fits into memory. So how many reads, how many seeks would we perform? And the question is, have you seen this answer before? Hint, hint. So I read the first block in R. I have to, so that's a seek and a read. Then I go and I read the first block in S. That's a seek and a read. And then I scan through S, because I have to do that for my inner loop. Read, 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 read. Those are all small seeks. And then I have to go to the second tuple in R. Well, S is already in memory, and one block of R is in memory. Do I have any more reads and seeks from reading S? Right, I'm done, right? So then I read the second block in R. I have a seek and a read. And then I scan through R, because every time I traverse S, I already have it in memory. So this is a very interesting result. So S is loaded once in sequence, one seek and B sub S reads. Outer loop traverses R and B sub R blocks, so 1 to 2 seeks. Again, that was accounting for our possibility that the disk head is already over R when it begins to be read. B sub R reads. So B sub R plus B sub S reads, and 2 to 3 seeks total. You guys recognize this? This was from the best case when we had room for both R and S in memory, which I think is just a marvelous thing. What this means is that if I can only fit one table in memory, pick the smaller one, and well, actually that's not entirely true. But if I can fit a table into memory, then I need to make that table the inner loop, because that will greatly reduce the number of seeks and reads I have. Okay? So that's one part of this. Yeah, now, like I have here, this is the nested loop join, and this is a very common optimization. MySQL does it because, of course, MySQL only uses nested loop, so it tries to squeeze every ounce of performance out of it. If the database can only hold one block of each table in memory, we have this problem that the inner loop is traversing this inner table once per tuple. And that's kind of stupid. Because if I have a block of tuples from R and I have a block of tuples from S, why would I only join one tuple from R against all the tuples in S? Why wouldn't I try to join all the tuples in R against all the tuples in S? That seems to make a lot of sense. So what we do is, again, one of those bizarre situations, this is one of the few bizarre situations, where adding more loops makes it faster. It's not common that you have that kind of situation in programming, but frequently when you're working with blocks of data, it does. So we'll try to join all the tuples from a block of R against all the tuples from a block of S. So this is block nested loop. And you can see here now, for B sub R, capital B being a block of R, and a block of S, and then you iterate through the tuples in that block and the tuples in S's block, and you try to join them together. So we added 2 more loops, and suddenly this thing becomes substantially better. Worst case read behavior of nested loop join. So now the outer loop performs B sub R block reads, and we're only traversing the inner loop once per block as opposed to once per tuple. So we've cut out a huge number of seeks and reads by doing this. Best case behavior, does it change? It will not change the best case behavior. Let me see if I have a comment about that. Yeah, so this is the worst case seek performance. Yeah, so block nested loop join doesn't change the best case behavior, which thankfully is the typical case because we have so much memory now, which is great. Okay, yes? So, you typically better by using more than one block? Yes, Another excellent observation here. We will talk about that optimization in a moment. But to give away the punchline, if I get a benefit by traversing R in blocks instead of in tuples, well, why don't I traverse R in multiple block chunks instead of in single block chunks? You get even more performance improvements because you have to scan S even less. So what we're talking about, and I'll just, we can go ahead and skip that slide when we get to it. If you can load all of S into memory, then you already have won yourself a huge benefit. And then, furthermore, if you can scan R in more than one block chunks, then you get even more benefits. And that's where you start getting a lot of benefits from read-ahead, because now you can employ a read-ahead optimization to get that additional data into memory so that by the time you're ready to look at it, it's already there, and you've basically parallelized the disk system's I/O with the CPU's processing of tuples. Okay, you've overlapped them, you've pipelined them. So yeah, there's definitely some big benefits here. So let's go ahead and explore this all. Seeks, inner loop traverses S sequentially, so once per loop. This is worst case, so we only have one block of S and one block of R in memory. We can't store any more than that. So we have to scan S sequentially, but now we're not doing it once per tuple, we're doing it once per block. So it's B sub R, and then outer loop traverses R in B sub R blocks. We have to keep going and getting the next block of R because we keep scanning S, so we get B sub R total seeks. That part didn't change. So the total number of seeks with block nested loop join, worst case, is better. Now here's another question for you. I keep saying, oh, we have tons of memory now. What situation would cause a system like that, our modern systems, to run out of memory for executing these joins? Let me give you a scenario. You have a class that you're teaching about database systems, and you decide to provide a database server for them to use. And all of the students decide to wait until 1 or 2 days before the assignment is due to do the data warehousing assignment. The system has 2 gigs of RAM, and the data set is half a gig. And you happen to be using a database server that can only do nested loop joins. All right, sound familiar? So when you have a situation where you have multiple concurrent executions of queries, the memory allocation or the memory pressure becomes so great that you have to start giving each query execution less of that memory. And it can get small enough to the point that you start running into these worst case scenarios. That's why we care about what's the worst case performance, even with systems where we have tons of memory. Because throw enough concurrent queries at it, you will hit that situation. And so that's a topic that we don't talk about like at all in 122. How do you actually allocate resources or assign resources to concurrently executing queries when you have one shared memory pool? That's a challenging problem to solve. Because what you end up doing is you try to design algorithms that do really well in the best case, but can scale their resource usage in some linear way, so that as the resource availability goes down, you can adapt to it in a hopefully graceful way, and then the worst case is still not horrendous. So this is the reason why we need to think about things like this, even though you running NanoDB will never need block nested loop. Okay? So these are the reasons why we need to understand these things. Any other questions, observations? Okay. So let's see. Best case scenario, so it's still the same as before, B sub R plus B sub S and 2 to 3 seeks total. So smaller table goes on the inner loop of the join. Worst case scenario, and this is where it gets interesting because you need to put the smaller table on the outer loop of the join. So you can imagine this weird kind of logic in the planner optimizer where you're like, well, I figured out the smaller table. Can I fit it all in memory? Yes? Okay, it goes on the inside. And I'll have the larger table on the outside because that's going to reduce the amount of disk seeks and IOs I perform. I can't fit it all in memory? Oh crap, now I need to put it on the outer loop. So you have to sort of figure out where do I stick it, and That's the other challenge is you put the smaller table on the inner loop of the join because you think you have the memory, and then concurrent queries come in, and suddenly you lose the memory you thought you had, and you end up with the far worst case scenario than you would have if you just stuck the smaller table on the outer loop. So you start to see that there may be benefit in the notion of reserving resources for queries. Like, I will give you this much now because I have it, and I guarantee you will never have less than this much space, just so that the query doesn't become horrendously non-performant. So you have to think about these kind of things. We don't, but if you're writing a real database, you would. Okay? Yes?
Is that what MySQL does?
MySQL does a lot of things along these lines, yes. It has to, because of the way that its join processor works. I mean, it's funny because it has one very limited way of joining tables, and so they can spend all their time and effort understanding that problem really well. But there's still things that are out of reach for MySQL because it only uses nested loops. And it primarily involves doing joins against derived relations, which is a very common thing in database queries. I will not get to hybrid hash join this week, we'll talk about it on Monday. We'll probably, in fact, just finish nested loop. So, but there's other algorithms that MySQL does not support, and therefore it's just always bad at certain queries. Whereas Postgres, Oracle, DB2, SQL Server can do those other join algorithms, and they're very good at those kinds of situations. Okay, so a few other optimizations. So we talked about reading it in multiple size blocks, multiple block size chunks. Another really weird optimization is that you can actually scan the inner table forward and then backward, which is weird, but when you scan it backward, guess what? So you're going forward, guess which pages are in memory, the most recent ones you accessed, and then you start going backward, and those are still in memory. So guess what? Fewer disk seats. That, if you're talking about a spinning magnetic disk, that's substantial. So that's a little weird. Okay, other join algorithms. What we'll do is we'll just wrap up this slide, and then we'll talk about the next time. The other join algorithms are much faster than nested loop join. Their best case is better. Their worst case can actually be as bad. But the thing is that the other join algorithms are actually more constrained than nested loop, which is, again, why we need to have nested loop around. So we call these other joins that involve equality tests equijoins. And probably 95 or more % of the queries that run against a database are equijoins. So the two other joins that we're going to talk about, and we'll talk about them on Monday, are sort merge, again, join based on sorting, big shock, and then also hash joins based on hashing. And like I say, they can only be used in specific situations, but since they're so common, people do natural joins or joins with a using clause or so forth. It makes so much sense to have these. And so I'm going to give you guys the opportunity to implement sort merge join. But hash join is going to be probably not worthwhile to implement just because of NanoDB's abstractions. Okay, any questions? All right, well, thank you guys for the feedback, and we will resume on Monday.